Hello and welcome back to the ongoing series of lectures on Printers Material Science 1. In lecture number 1 and 2 together combined, we have completed colloids, which was the first unit in Printers Material Science 1. In this lecture, we will we'll be starting to talk a little bit about polymers and their importance, their applications, their some of the important properties. Polymers is basically the second unit in Printers Material Science 1. See, the interesting thing is, as I told you earlier in the earlier lectures, also in the first and second lecture, I think that I chose colloid as the first starting point before even going into the other courses, because without having a working knowledge on colloids and polymers and their properties, we will not be able to really identify and analyze some of the applications which they have in the graphic arts industry. So, since we have developed the idea on colloids, colloidal systems are basically, you can say, they are physical properties. But when we are talking about, we will see the same things. We talked about gamma arabic, we talked about some starch, gelatin, various gels, emulsion, inks, all these things we talked about in the chapter on in the lecture on colloids. We will see in this lecture also that the same things are again coming back. The same we will be discussing the same materials, but in the previous lectures we talked about their physical characteristics, especially in relation to their colloidal behavior. So, colloidal property is basically physical property of the material. In this lecture, we will see some overlap in the materials on which we will have our discussion on, but we will discuss their polymeric nature and the properties that these materials have, which are in relation to their chemical properties. So definitely, once the chemical properties change, it is going to impact their physical behavior also. We will see that also. But when we talk about polymers, it actually has a wide application, and it's not possible to for me to teach you polymers in 2 or 3 lectures like this. It's a different science and technology altogether. People study, people research on polymers. Polymer is perhaps one of the most important topic in science and technology, on which there is a huge industrial importance attached to in the modern industrial world. So that way, anything and that you see around you perhaps has some form of polymer science and technology uh, to it. From the very first thing that you wake up in the morning to do, that is brush your teeth, the brush that you are using is made out of a polymer. The toothpaste you are using is packaged inside of a polymer. Till the time you go to sleep, everything that you use, that we use in our daily lives today, has some form of polymer in it. So it is something, polymer is something which has touched our lives in a lot of ways, and it is perhaps one of the most important materials that we use in the graphic art industry as well. So, without further ado, let us take a look at what polymers are. And this again, already said in the previous lectures also, these may be, aligned more towards chemistry, but I'm not really here to talk about the, core chemistry part of it, because that is not our subject. This is not a chemistry class. Our intention here, I want in the end of the class, in the end of the lecture, you, the student, will be able to first identify the different polymers that we use in the graphic arts industry, and determine a suitable polymeric material, whatever it is, for a given job. And if there is any problem, there is any unwanted consequence during the print production, related to some of the polymeric materials, you will be able to do the root cause analysis. So that is our outcome. We will not be our outcome is not to prepare some new polymers and write chemical structures. That is not the outcome. So you will be seeing, I will be showing you some big formulas and all this. Don't get afraid of it, because that is really not our concern. Our concern is the application part, and the uh, and to identify the problems that arise out of various print production and ancillary production methods related to polymers. So that is the important thing to take away from this lecture. So without further ado, let us take a look at some of the things that we will be talking about. So before going into the details of the types of polymers and the uh, various forms and the classification of polymers, let us first understand what really is a polymer. So poly means many, right? So it has got something to do with many things. So what are these many things? Many number of smaller units known as monomers. Okay, so consider this example, right? You all know this. This is what? Pause the video, give yourself the answer to. This is ethylene, right? We all know this. Under normal circumstances, under normal conditions of temperature, pressure, etc., this is basically in the gaseous state, right? But when it is subjected to a different set of conditions and in presence of certain catalysts and everything, it transforms from the gaseous material to a transparent solid which is known as polyethylene. So, what is the difference between the structure of both the things? So, this is basically your ethylene. So, what is the structure of polyethylene? It will be something like this. So, what really happened? So, here in the first case, you had only a single molecule of uh, ethylene, right? But once it is subjected to certain set of conditions and all this, its characteristics are changing, its physical properties are changing. Why? Because multiple such ethylene molecules are getting connected. First of all, you see this sorry, this double bond is broken, right? Now, what happens when this double bond is broken? A free radical is generated. So, we'll be talking briefly about the processes through which polymers are made, but just to give you a brief idea here. This double bond is broken, releasing a free radical. Now, these free radicals are very reactive. So, this free radical goes from this molecule, shifts from this molecule and goes on to attack another ethylene molecule. Consequently, what happens? That double bond also breaks down. So as soon as you have multiple such molecules where these double bonds are no longer present and they are all, uh, uh, you know, very reactive, what happens? They all combine with each other. So this N means multiple ethylene molecules combine and forms bond with each other to form from ethylene polyethylene. I hope this is clear. So, in this scenario, if I call this as polyethylene and this is definitely ethylene, so what can we call both these molecules in general? Can we call this particular molecule as polymer and this particular molecule as monomer? Mono means one. This contains only a single molecule of ethylene. But when under certain circumstances they all combine together with each other and you know uh, changes their physical properties, what happens? They form something which is known as polymer. Another important point that I would like to mention over here is this property of N over here. So you may ask, so what will be the value of n? It's a legitimate question. Now, the value of n varies from one polymer to the other. This n is referred to as the degree of polymerization. This is referred to as the degree of polymerization. Normally, if you count, the molecular weight of this ethylene molecule is around 28. So, what will be the molecular weight? So, if I write over here, what will be the molecular weight of polyethylene? What will be the molecular weight? It will be some multiple of 28. It will be n into 28, right? Because multiple ethylene molecules are combining with each other to form polyethylene. This n, as I already told you, this n is basically known as the degree of polymerization. This is very important because this determines the degree of polymerization, determines multiple properties in the polymer, its flexibility, its tensile strength, glass transition temperature, and all these things are determined by this. The length of, so if we can formalize this, how can we say what is the degree of polymerization? The length of the polymer chain is specified by the number of monomeric units that are being repeated. This number is referred to as the degree of polymerization for that polymer. Okay? Now, the question is, why study polymers at all? Why is it important? You see, almost you see in any part of the any printing process, you will find invariably that in all the processes in our industry, we use some form of polymer or the other. For example, my small exercise for you to find out is I'm giving you some processes. So, for example, in offset process, actually in offset process we use so many polymers in so many stages, not just during the printing operation, but even before it. So maybe during the plate preparation, maybe during the film preparation, maybe during the actual printing operation in the printing machine, maybe after printing, post printing operation. So can you just make a list of polymers that are used during the offset process? I know you do not know all those all the materials that may be used, but till now, whatever you have seen, whatever you have done in the laboratory work, whatever you have studied, from that knowledge and experience, can you just list all the components or polymeric components that are used in the offset process? Similarly, for the flexo process, see, you may not be used to or acquainted with running a flexo machine. I know that, but you know all the components of the flexo machine. In basic printing, you have been taught all these things. That is what is offset printing, flexo printing, screen printing, gravure printing, all these things, schematic idea or fundamental knowledge about all this stuff you have. So from that knowledge only you will be able to explain or just list the point of polymers, number of polymers that you see in this process. Similarly for gravure process and definitely for screen printing process. In all these things, can you just prepare a list of polymers that we use commonly in this all these printing processes? Okay, so I think this would be a good exercise for you to just before we go any further into understanding the polymers and their properties and structures and all that. I think you will find it interesting to know what all materials are already being used, whose properties and whose application you need to know, and why. Only when you find the answer to this question, you will be astounded at how many polymers we use in all these processes. So I think if you can find out the answer to this question that I just asked, you will be able to know why study polymers at all. Okay, so because it's very important, at least in this stage, this is not a general course, this is a technical course. So for you to ask this question, why study this chapter? Why study this particular topic? It's very important. Now, why this is not a chemistry class. This is not, you are not doing your graduation or diploma in chemistry. So why study all these chemical things? There is a reason behind it. So I'm asking you yourself, will be able to find the answer to this question. Why study polymers? I already gave the answer for you. Why study colloids in the previous lecture. So for you today, it's your job to find out why study polymers, and send me your completed sheets. You may just jot it down, take a photograph, and send it to me via the Google Classroom platform, or you can just prepare an Excel sheet and send that also, right? So moving on now, as I already told, that there are various, now we come to an important topic which is known as the classification of polymers. How polymers are classified and why they are classified in such a way, this is actually quite interesting and quite important to understand. Based on the source or the origin, they are classified into natural and synthetic polymers. So here, before we move any further, can you name any two natural polymers that you know of, or and any two synthetic polymers that you know of? Just I'll be saying all the answers, but just before we begin, can we name, because for you to answer the rest remaining of the classification types of polymers, that will be difficult. So just from experience or just from prior knowledge, will you be able to name any two natural polymers and any two synthetic polymers that you may have used? We all have used natural polymers as well as synthetic polymers. So will you be able to name some of the two each from each category, based on the, when we classify the polymers based on their origin or source? Okay. Next, another way to classify polymers is basically its structure. One is linear and one is branched. So a typical linear structure will look something like this. So you'll have carbon atoms like this arranged, so it will be like this. But in a branch structure, you will have something like this. So everything will be covered by N, right? Something like this. So there will be something, and it will be branched, highly branched. So be giving examples of each and every type of polymer, but just by structure, the way the atoms are arranged in the within the polymer, they can be classified into either they can be linear or they can be branched. Next method of classification is synthesis. The you can say the way in which it is prepared. So first we will be starting, our starting point will be based on synthesis. We'll be starting from here. There can be two types of polymers based on the synthesis. One is addition and the other is condensation. So what I'll do is, I'll not just go on stating all the other polymers and their types and how they're classified. I'll be coming back to this classification as we go on and move progress in the course, progress in the particular unit. So based on the types of repeating units, if the same type of repeating units are there, then it's homopolymer, different than so I'll not be stating all this just at this moment. So as we go ahead, so first let us start with the polymers based the classification of polymers based on the method in which they are synthesized. Either they can be addition type polymers or they can be condensation type polymers. So let us start in that way, otherwise everything might seem too much to take in for the first class. Okay, so first, okay, so here we begin with the not the I think the synthesis, but the nature of the structure of the polymer. So here you see this is you can see this is a linear polymer. So normally what happens during any polymerization reaction, there are three stages. One is initiation, one is propagation, one is termination. So during the initiation phase, in the presence of a catalyst or the presence of external factors, what happens? The molecule or the monomer, this is the monomer unit. So you can say that this monomer unit will be repeating itself, right, in combination with something else maybe. So during the initiation phase, what happens, because of the presence of some catalyst and external factors, this monomer units starts to liberate some free radical. This free radical then transfers onto and attacks another molecule, right? And this becomes very reactive. Whenever there is a free radical being generated, the free radicals are very reactive in nature, and whenever they attack some other molecule, uh, there are some chemical changes happening. So you can see this free radical that has been generated here is attacking the double bond, carbon carbon double bond over here, and you get something like this. So you are sure that this is your repeating unit. Repeating unit is, like in that case, in the ethylene case, what was the repeating unit? This was the repeating unit, right? So in this case, in this particular polymer, you see this is basically your repeating unit. So this free radical now is sitting over here. Then after this, it will attack another such molecule, right? Once it attacks another such molecule, the same thing will happen, and you will see the chain. We say this is the polymeric chain. This polymeric chain will then start to elongate. The method in which, the structure in which they elongate, see, this is elongating in this particular direction in a linear fashion. That is why this is known as linear polymer. So what happens in the three stages of polymerization reaction, in any polymerization reaction, be it your oxidative polymerization, which happens during the drying of offset printing ink, or be it during the drying of UV curable inks, which happens during UV curable inks that are being used during various types of printing mechanisms. These are the common three steps which is followed in case of any. In the next phase, what happens is that once the free radical attacks the monomeric units and they become reactive, this chain starts to get elongated. So one will attack another, one free radical will attack the one monomer, and after that has the double bond opens up, then it will start to attack another double bond, another monomer. So like this it will propagate. So propagation means acceleration in the process of polymerization, and finally when there are no more free radical, when there are no more monomers to attack, that means all the monomers has been in the system has been utilized, so you cannot increase the length of the polymeric chain. During that time, what happens, the reaction comes to a standstill. This last phase is there by known as termination of the reaction. Okay. Next, you see this is okay, this is another example. uh, yeah, so instead of, yeah, okay, so here you can see that this particular example is we are using vinyl chloride to be precise as the monomeric unit, and uh, ultimately in the polymer what we are getting the PVC, right, or the polyvinyl chloride. Can you tell me some of the examples, some of the applications of polyvinyl chloride, not just for printing purpose but for other purposes also in our daily life where we use PVC? So this is a question for you. Now in this scenario what we see is, after we have seen the linear increase or the elongation of the polymeric chain in a linear manner, now we come to another type of classification of polymers based on the nature in which they are synthesized. So this first type of classification based on synthesis is known as addition polymerization. So what is addition? Addition is just the, like the previous one I showed you, previous example I showed you in the previous slide. You see the monomer units are just getting added with each other, like the ethylene molecule, monomeric ethylene molecule were adding with each other with the help of a catalyst. So similarly here also you see that the monomeric units are adding up with each other. This is known as, this type of synthesis is known as addition polymerization. Okay, so here you see you start with the vinyl chloride monomeric unit, and after polymerization you get this large chain of polyvinyl chloride, which is basically, you can say, type of addition polymer, because the process is adding up multiple monomeric units together to form ultimately a polymer. Okay, I hope this is clear. And the reaction mechanism I have already shown you in the previous slide. So in the next type of polymer, what we will see is, this is actually a very important, not just for this one, condensation polymerization, based on the type of reaction or based on the type of synthesis. This is another form in which we can classify polymers. Like in the previous one, we saw that addition polymerization, where the monomeric units were just getting added up together. In this type of polymerization reaction, we will see the monomeric units are uh, elongating, or there is polymerization, but the mechanism in which they are elongating or the polymerization is happening, that is a little bit different. So normally what happens, this is basically a kind of ester formation or amide formation. Ester formation is very popular because esters are normally we call it trans esterification reactions when we prepare some uh, resins in that are to be used in various types of ink. So in those type of reactions, what happens, we usually take a diacid and a diol, or a maybe a diamide if we are creating a diamine, if we are creating an amide instead of an ester. So here we are using a diacid and diol. Why diacid? Because you see there are two acidic functional groups and two diol. So normally what happens is, there is these two undergo a chemical reaction, and what happens, since this is condensation, that means there will be an elimination of water. So you see, this is the water molecule that gets eliminated, or in some other cases there may be elimination of some other smaller molecule also. So this, once the water molecule gets removed, then after this process continues to take place. So once the water molecule gets removed, then these two molecules, this one, this diacid and diol, they combine with each other, and then once the first water molecule is removed and these two molecules combine with each other, similarly other molecules also react with each other to remove water or some other small molecule to finally form this particular polymer, where the polymeric link is here. What type of polymeric link? See, if here OH and H is removed, then what will be the polymeric unit? A polymeric link. This is what? This is what type of functional group? COO. This is an ester functional group. That is why this is known as esterification. This particular reaction is known as esterification. And normally, when two molecules, it may be either a diacid diol or diacid and diamine. In case of we are making here, in case of diacid diol, we are making an ester, but in case of diacid diamine, we will be making an amide. So depending on whatever the requirement is, you can choose these type of polymers, which are basically known as condensation polymers. Why condensation? The polymerization is taking place after molecules recombine due to the removal of water or any other small molecule. That is why this is known as condensation polymer. As I was saying, that this is a very important reaction in kind of your resin preparation in different types of inks that we use, be it in offset, be it in your liquid ink. So there are various types of resins which are prepared in this way basically. So that is why condensation polymers have multiple utilities in various types of industries, not just in our industry but in various industries in general. Okay, I hope this is clear. Next, so yeah, okay, so these are the same. Yeah, this is another example as I was talking about. So here you see, instead in the previous scenario where we saw that there is a diacid, here is the diacid and there is a diol, so that you are reacting between acid and alcohol to create this ester. But what if you are going to create amide? Then you have to react with the diacid and diamine. So there finally this is the what do you get? You get the amide group, right? So that is your link between the your kind of the monomeric units that will link all the monomers together. Okay, so this is another type of condensation polymer that you need to know about. Next, as I told you, that there is another type of, based on, as we first saw linear polymers, and we saw also based on the type of synthesis also, that there is two types, that is addition polymer and condensation polymer. Now we come to another type of structure based on the another type of polymer based on the structure, which is known as branched polymer. Here, normally you see this is basically the type of polymer which it's a basically photopolymer, because here you see the multiple units are attaching themselves together. In what fashion? In this branched fashion, right? In this branched fashion, they are not linear like polyethylene or PVC, etc. They are branched. So depending upon how well they are branched, their properties will vary. The paint that normally you see in your home, these type of wall paint, I mean these type of paints are highly branched. Even our printing inks, offset printing inks are kind of has this branch structure, because normally you see in our offset resin preparation we use highly branched acids and alcohol, not acids really but alcohols. So there you see multiple, maybe a few hundred number of alcohol functional groups in those uh, reactions. So what happens ultimately, the nature, so normally you see the diol over here, instead of diol we use alcohols which have few hundred number of alcohol functional group. So ultimately, after preparation or after synthesis, the structure of the polymer becomes not linear anymore but becomes branched. So there are advantages and disadvantages to both the things. But what important property branched polymers have is the kind of film forming ability. So what examples did I give you of branched polymers? I gave you examples of wall paint and the printing ink. So in both the cases you see, I don't know if you have heard this in the paint ads. You see, you will find this cross-linking polymers. Cross-linking is this one. These are cross-linked polymers. So this will form something which is known as the interpenetrating networks actually. Okay, that means it will be highly networked, and it will, the ability to form thin films for this polymers is very high. So that will be very much flexible film, and that will also provide a lot of stability to the material on which it is forming, and it will have a good adhesion to the material on which it is being either painted or printed. Okay, I hope this is clear. Next, what we these are some of the other examples. I'm not going to all the details here. I'll come back to homopolymers and copolymers in a bit, because I have to cover that in a little bit detail. But now let us talk a little bit about the various types of polymers based on their source or origin. As I told you, in the, if you can remember the type of classification based on the origin, how did we classify the polymers? We classified into two types. One is the natural and the other one is the synthetic. So let us first, and I gave you one task also to can you remember any two types of can you recall any two types of natural or synthetic polymers that you use, that you may be using in the daily life? So now let us first proceed with the natural type of polymers. So these are all, obviously these are naturally occurring polymers, but yes, not it is always not necessary that when we talk about natural polymers we will use natural polymers in in their native form. We will have to modify natural polymers, because the properties that we want may not always be there in natural polymers. So we need to modify their properties in certain ways, and then finally we can use it for our various purposes. So one of the such example is rosin. So rosin is basically an acid. So rosin, in the prior times, rosin was used. It's basically obtained from the extrusions of pine tree. So it's nothing but multiple acids in polymeric form. So rosin was used in printing inks, but some of the properties of rosin made it difficult for it to be used. Okay, so what we did, we modified it. We modified rosin using various materials, with maybe malic anhydride, with maybe ester, with maybe phenol. So all these materials were used to modify the behavior and the structure and the property of the rosin to suit it for our own purpose, for using it so that it can be used in various types of inks for certain, that will meet certain standards or meet certain specifications. So this is an important point for you to remember, so that natural polymers, yes, they're naturally obtained, their source is natural, but not always it is necessary that we'll use it in their native form. We may have to also modify their behavior by reacting them with some other materials. So having said this, now what I'll do, I'll just list down some of the materials, some of the naturally occurring materials that uh, we normally use in our industry. So first comes casein. I think you know this casein term from before, because this is a natural resin which is obtained from, you see, milk. It is an ingredient in plastic and synthetic resin, and during the preparation of light sensitive coatings for our plates, we normally mix this with ammonium dichromate. Can you tell me why this is mixed with ammonium dichromate during the preparation of light sensitive coating? If In order to answer this question, you need to go back to the colloids class. You need to remember what I taught in that colloids class. What did I say? Normally, light sensitive coating, which is the light sensitive part in the coating? The ammonium dichromate, which is kind of your lyophobic colloid in nature. So, if you use it in some other medium, it will not have any affinity towards the medium. That is why some protein is used. It may be casein, it may be gamma arabic, it may be PVA, whatever it is. There should be some material which is giving that protection to the lyophobic colloid ammonium dichromate or silver halide, whatever it is, silver halide in case of film photography, to prevent. Next type of natural polymer that I would like to talk about is basically your cellulose. Now, cellulose is basically a type of polymer of the glucose. Glucose is normally C6H12O6N. Cellulose has a structure of C6H10O5N. So whenever we are talking about polymers, we always use the monomeric unit to refer to the polymeric structure, because the polymeric structure, writing the polymeric structure doesn't mean anything. So this is basically your normal structure of the cellulose fiber. So cellulose is actually obtained in the trees, the wood part of the tree, and it has multiple applications in our field, especially in paper, and some definitely it has been modified to be used in modified synthetically, I should add, in various types of inks and various types of lacquer varnishes that we use during the printing operation. But its main use is in the paper industry. Cellulose is basically the fiber which has got this property of swelling up when water is added to it. Why? Because you see, there are this hydroxyl functional groups over here. These hydroxyl functional groups, which may be free or maybe not, they form hydrogen bonds with water, and as a result of which, you see, cellulose fiber has a tendency, whenever if you take any piece of paper, especially newspaper, which is very absorbent in nature, you see, it's very easy to wet that particular paper. Why? Because not all paper is the same, so that is why I specifically talked about newspaper. So what happens is, this cellulose fiber has a tendency, natural tendency, to absorb water via these hydroxyl groups. Hydroxyl groups will form hydrogen bond with water, right, and it will swell up, and it has got poor dimensional stability. Dimensional stability means, this is a term which is going to come back very often. Dimensional stability is the ability to withstand, for any material, be it a paper, be it a film, be it any other thing, for any material to maintain its dimensions in spite of some external forces. So for example, when I say that the dimensional stability of cellulose acetate is strong, that means cellulose acetate is the next type of polymer that I'm going to mention. So cellulose acetate is basically having strong strength, tensile strength, or that elastic behavior, so that when it is deformed, it will again come back to its original form after the deformative forces are removed. So this is what dimensional stability is. Dimensional stability in paper, very important. Newspaper does not have a very good dimensional stability. That is why there is fanning out problem and all this. You will see that these type of problems, how to counter this type of problems in newspapers. When you go into your planographic printing techniques courses, you take those courses. So normally what happens is, uh, due to absorption of water because you see there are these hydroxyl groups, functional groups present in the cellulose fiber, which is the main component of paper, they try to swell up, as I already told you. But during the preparation, in order to counter this effect of swelling up of the paper, in order to counter this effect, various types of materials are added to paper and various types of processing is done. Beating is one such process. When we will talk about paper making process in PMS2 class, we will see this in great detail. Beating is one step. Adding some internal sizing agent is another one. So coating the paper is another one. So there are multiple such techniques using which we can basically prevent or somehow reduce the amount of dimensional stability that happens in paper. Okay, so for this I think for this class I think only the purpose and application of cellulose is essential. Another, as I told you, cellulose acetate. It is basically cellulose acetate is obtained by acetylating your cellulose. Like in this case, it has been done with H2SO for an acetic anhydride. Its main purpose is used in films. It has good dimensional stability, but the problem with cellulose acetate is it may tear very easily. So you will see, you may find it very strange that I'm saying the dimensional stability is high, tensile strength is maybe high, but its tearing resistance is poor. We will talk about this exact point when we discuss paper, but for here, for at this stage, I think this much information is enough for you to remember. Next we have cellulose nitrate. Cellulose in itself is not soluble in water or anything, but it is neither in acid or bases, but it may be reactive. It may be made reactive uh, under certain circumstances, where it reacts with nitric acid, sulfuric acid, all this to create cellulose nitrate. Cellulose nitrate is not referred to as nitrate in industry. It is referred to as nitrocellulose. Nitrocellulose is very much important component during the preparation of lacquer based liquid inks. It is one of the primary components, one of the primary, you can say, this is a type of resin which is used, or this is another example where you see cellulose is naturally occurring polymer, but it has been modified using synthetic methods to create something, a synthetic polymer, which is basically used in the preparation of resin in the printing industry. Especially this is nitrocellulose is especially used in the liquid ink industry. Okay. Okay, another type of example where cellulose has been modified using synthetic materials to suit particular purposes is cellophane. So I think you have all known what cellophane is. During we have used cellophane during our art projects, maybe in school or something. But cellophane is nothing but regenerated cellulose with the help of sulfur. It has been modified with the help of sulfur. But the problem with cellophane is that it is soluble in water, and most importantly, it swells in water. That is a big problem with cellophane. It is soluble in acetone and insoluble in ether and toluene. It has good sealability property. Due to this good sealability property, it is most of the times it is used for lamination purposes. So in our art projects also, remember we used to you know cover our artwork or the album covers with cellophane paper, cellophane films. So why did it happen? Because it had good sealability property. Okay, that is why today cellophane is extensively used as laminating material in the packaging industry, as the covering material after. So, for example, you have printed something. So after it has been printed, it will be covered with the help of the cellophane. Okay. Next, we have another example, another type of polymer, which is dextrine. Dextrine is actually obtained from starch. We will discuss what starch is, but it is actually obtained by again acetylating starch and uh, then hydrolyzed. So dextrine is basically starch molecules together, they form this polymeric structure. They are very much soluble in water as starch, but even more soluble in water because of the excess, because it is undergoing hydrolysis process. That is why the number of hydroxyl groups that you see over here, number of hydroxyl group, free hydroxyl groups, not the bonded ones, they are increasing manifold. That is why its solubility in water and the, its ability to swell water increases a lot. Normally what happens, they are used in, as adhesives for the, back adhesives for postage stamps and envelopes. You see, sometimes they are used for those type of adhesive work. Next, we have ethyl cellulose. Again, you can see that cellulose, this is cellulose which has been modified again to suit particular purposes. Ethyl cellulose, just like your nitrocellulose or cellulose nitrate, is which was modified using nitric acid and sulfuric acid, cellulose modified by those acids. They were used as nitrocellulose was used in lacquer-based printing, liquid printing. Ethyl cellulose is also another type of resin that is used in uh, your lacquer-based varnishes and liquidings, right? Next we have gelatin. Yes, don't go by all these things. So I'll just change the slide. Yeah. So this seems to be appropriate. This seems to be better looking than what gelatin really is. So you see, gelatin is nothing but a kind of protein. It is obtained from animal hides and, skins and fats and all this. So it is nothing but the protein, right? It contains the protein collagen, which when it is normally treated with acid, then heated with water, then during at this point, remember in the colloid chapter also I told how gelatin, when it is heated in water, it passes on in the gel form. So when you acidify it and then treat it with hot water, it the collagen in it, collagen is basically the protein which is found in all animals actually, even different types of animals, collagen is found. Now this at this point, when it has been acetylated and then finally heated with water, the collagen then passes into the gel form. And what is interesting to find here is the fact that the isoelectric point, if you remember isoelectric point from our from our discussion on colloids, the isoelectric point for gelatin is 4.7. So that means gelatin normally has got this tendency of absorbing water. As you remember, that gelatin is basically an elastic gel, not a rigid gel like salicylic acid, but it is basically an elastic gel. What does elastic gel means? That means it has the ability to absorb water. When it absorbs water, it becomes it swells up obviously, and depending upon this ability to absorb water depends upon the isoelectric point of gelatin. Isoelectric point of gelatin is somewhere around 4.7. So anywhere above the 4.7 value or below 4.7 value, gelatin starts to absorb water. Normally at 4.7 it is stable and it behaves in a proper way, instead of the being in the elastic type of gel that we are normally used to see gelatin as. Now, gelatin has multiple functions in our industry. The crude liquor that contains gelatin, that is obtained from chemical treatment of hides of and skins of dead animals and bones of the dead animals. First, they are bleached with sulfur dioxide, then mixed with borax and formaldehyde, and then concentrated. This syrup or this liquor is sometimes used in the food industry, because this basically, see, the basic idea is you acidify it to purify. You will see how it is acidified. First you purify it by acidifying it, and then you heat it in water and hydrolyze it maybe. During this process, what happens is the collagen, this protein, they pass on to the gel state, and as soon as they pass on to the gel state, we have obtained that gelatinous material. This is extensively used in the food industry, obviously, because this is a naturally sourced product. This can be eaten or taken for human consumption. But apart from that, we also have some example of gelatin where I do not have. always going back to the next slide in the hope that I have that picture of the photographic film that I showed, that I unfortunately in this slide I do not have that photographic film. If you remember, I'm just repeating it, although I have already explained it in the previous lectures when I was talking about colloids. Gelatin is basically another type of, since it is a protein, definitely it is a lyophilic colloid, right? So it has got this ability to protect what? The lyophobic colloid. Which lyophobic colloid? Where is gelatin used in our industry? In photographic films. In photographic films, gelatin is basically the forms the emulsion of the film, in which the silver halide is basically dispersed within this gelatinous structure of gelatin. Okay. What would have happened if gelatin would not have been used? All the AgX would have coagulated and precipitated at the bottom of the film. So that would have not served our purpose. To keep the silver halide dispersed uniformly throughout the film, gelatin is used as a protective colloid, or the lyophilic colloid, which encapsulates the the lyophobic colloid and prevents any sort of electrolyte to attack the lyophobic colloid and neutralize it, and hence prevents its coagulation. Okay, that is the importance of gelatin in our industry. Next, this very important part, which is known as gamma arabic. Now, gamma arabic is basically obtained from the barks of acacia tree. Now, it is normally a mixture of various metals like potassium, calcium, magnesium, and its salts in the of arabic acid. Now, arabic acid is basically a copolymer. Copolymer meaning the different types of repeating units are there. Copolymers of mannose and galactose. Their molecular weight is very high at around 42,000 in comparison to some other low molecular weight polymers that we saw earlier. It contains multiple carboxyl and hydroxyl groups in the molecule, and acidification, normally what we do is we acidify this gamma arabic to form arabic acid. Its application is in the fountain solution. I'll explain why. Now, acidification of with phosphoric acid reaches the or takes the pH of the gamma arabic to around 3, so which is highly acidic, and it liberates all the free carboxyl groups, and it decreases the solubility of the your gamma arabic in water. Now, if gamma arabic, which is used in the fountain solution, what is fountain solution first of all used for? Fountain solution is used, I'll be talking about fountain solution and the various properties and the functions in the coming lectures, but just to briefly point it out, fountain solution is used to give a uniform coating, as I told in the previous lecture also, on top of the non-image area, so that it will refuse the ink in the non-image area. Now, if this gamma arabic, which is used extensively in the fountain solution, this gamma arabic is soluble in water, then you will find that the purpose of desensitization or forming a uniform film on top of the your non-image area, that is failing. So what happens is, normally gamma arabic is used, I think I have a picture, yeah, gamma arabic is basically acidified, right? Gamma arabic is, so this is your gamma arabic, right? Because this is a calcium salt of arabic acid. So this is, you can say this is the gamma arabic. This is acidified with phosphoric acid. Now what you obtain is basically a acid, right? What will be the difference between this one and this one, you might ask? So I'll explain the difference as we move on in detail, as we move on to the next lecture on fountain solutions and water. But what will happen is, if you see, if this is your non-image area, so this is your non-image area of the plate, right? What is going to happen? This is your acid molecule, arabic acid molecule, right? This will settle on top of the non-image area. This is found, arabic acid is found, or gamma arabic is found in the fountain solution, as I've already told. This will settle. Don't worry if you are not able to fully capture the idea of what fountain solution is, what all materials goes into the preparation of fountain solution, you need not worry about it, because we have not yet covered fountain solution at all. I've just to explain individual materials like arabic acid, casein, cellulose, all this, just to give you a brief overview on the on the usage and application I'm saying on this, but I will take, you know, in detail classes on all these materials as we go along. Okay, so this is basically your arabic acid molecule, right? What happens is they settle on top of the non-image area. Now this hydroxyl group, they form hydrogen bond with water. So what does it mean? It means this arabic acid is actually pulling water on top of the non-image area to form a uniform film on top of the non-image area. For water formation or application of water or keeping a uniform layer or film of water on top of the non-image area is very much important. Why? Because if there is lack of water in the non-image area or fountain solution in the non-image area, then ink is likely to get into the non-image area and it will lead to the creation of scumming problem. Ink in the non-image area problem is scumming problem. Okay, in order to prevent this, we need to ensure that during all types of preparation, all types of print, during the entire print production method, we need to ensure a uniform film of fountain solution on top of the non-image area, and the fountain solution contains gamma arabic acid, water, and alcohol, apart from other things. But these three are the primary components. Alcohol reduces the surface tension of water. Gamma arabic helps in desensitization. This process, where gamma arabic or arabic acid pulls water and ensures a uniform, distribution of water throughout the non-image area at all times, is the desensitization process. Or this is how the non-image area in the plate is desensitized, and that is why I am saying gamma arabic should be acidified with phosphoric acid in order to liberate its free carboxyl group, so that it does not get soluble in water. If gamma arabic becomes soluble in water, it goes away, right, away from the plate, but it has to stick to the plate so that it can pull the water by forming hydrogen bond with water on top of it, on top of the non-image area. This is very essential, and sometimes you will see the plate is gummed. You see in the industry they use gum up kora. So gum up kora maneই হচ্ছে যে you add gamma arabic to the plate and as well as in the fountain solution, not really the fountain solution but primarily to the plate, so that the non-image area of the plate remains desensitized throughout the print run. I hope this is clear. Next, this is the last type of natural polymer that we'll be discussing. Starch, I think you all know. It is another form of polymer from the D-glucose family. So it is basically the N number, the degree of polymerization somewhere around 30, and it is insoluble in water, but it forms, as you can see, there are free hydroxyl groups over here. It will form hydrogen bond with this water. It is normally used in the preparation of adhesives and in the lamination industry and the packaging industry, and also very importantly, starch powder is in the powder form, solid form. Basically, they are used in the preparation of anti-set of powder. You know what anti-set of powder is? So, for example, you are in sheet fed offset process. You are printing. See, suppose one sheet is printed and kept on top of other. So there is a stack, right? I think you have seen the basic structure of our PO25 machine or a sheet fed offset machine. So one paper is stacked on top of other. So this is a freshly printed sheet on which, on a matter of fraction of second, another printed sheet on which the lower portion of the sheet above is unprinted, but the upper portion of this sheet is printed. So what is going to happen? The ink has not dried properly. Printing inks dry via oxidative polymerization. It is another type of addition polymerization reaction, but it is basically with the help of ionic catalyst. So it takes a longer amount of time, maybe 8 hours, 10 hours, maybe even a day. So during that time, when within a fraction of second the freshly printed sheet is falling on top of a freshly printed sheet, what is going to happen? The ink film is still wet. There is a chance that this ink film will stick on the back side of the paper which is fallen on top of the sheet. This type of problem is known as set off problem. Ink setting off from itself and reaching onto the back side of the sheet on top of it. This is known as set off problem. In order to prevent this problem, we spray a powder which is known as anti set off powder on top of all the sheets before it is stacked onto the delivery. During when it is taken by the delivery grip by the your delivery grippers onto the delivery section, before it is stacked, we spray it. During the delivery section, there is a sprayer which works towards spraying the anti-set of powder on top of the sheet. What happens? This anti-set of powder, the particles of the anti-set of powder, coalesce with the ink and prevents their transition from the sheet onto the back of the sheet, which is falling on top of it. This is known as set off problem, and in order to prevent it, we use anti-set off powder. In that anti-set off powder, starch is an important component.